Hello and welcome to my video about orbital dynamics. So there are a couple equations that we have been looking at in the last couple videos. So we've got the acceleration, centripetal acceleration formula here, and we have the velocity, tangential velocity to a circle there, and we also have the force, centripetal force equation right there. Now, honestly, these are the only two equations you really need, because actually, let me do this, because this red equation is what creates this equation up here. Okay, and once you have those two equations, this creates this one down here, and this creates this one down here. So really, we only have the purple and the red equations that are new. Yeah, we're given more equations than that, but really it's just two new equations. And this is what we've been given over the last couple videos. Now, in this video, what we're adding to that is that we have three situations. We have if it is FC equals FG, then it will have a stable orbit. If FG is greater than FC, the orbit will decay, meaning if gravity is stronger than the centripetal force has to be, then it will crash into the planet or decay. So if FG is greater than FC, and if FG is less than FC, so FG less than FC, then the orbit will expand and the satellite, wow, that's beautiful, will eventually leave the orbit. Okay, so those are kind of the three different situations. So let's take a look at what that means. I will say that normally we're going to be asking this stable orbit question. The other two are just, hey, if it doesn't have a stable orbit, what happens, right? So you will have to know about these other things, but the middle situation, that equals FG, is the real most important one. So here is my little picture of what that looks like. Okay, so here's the Earth. Okay, here is an asteroid. All right, I don't know how to spell anything, so sorry. So we have three situations. Okay, we have the blue situation, we have the purple situation, and we have the green situation. So if the asteroid is coming towards Earth, and it's not going to quite go directly towards Earth, basically nothing goes directly towards Earth, the chances of that are, pun intended, astronomical. So the asteroid's going this way, and if it has a certain speed, it will be, if it's a certain distance and speed, it will actually enter a perfect orbit. Now, this is very, very unlikely, right? What are the odds that the asteroid has exactly the right velocity and exactly the right radius away from the Earth? It's very unlikely, right? What's more likely is that the asteroid is too fast, right? This is the most likely situation. It's too fast or too far away, and so yes, it does get bent by the Earth's gravity, but that's all that happens. So this is kind of what that path could look like if it's going too quickly to get sucked in towards the Earth. And then the next most likely, or what happens when an asteroid actually hits the planet, is the asteroid is actually going to get sucked into a decaying orbit. So it may even, here's the thing, it may even orbit the planet once or twice before crashing down. Now, mine are exaggerated, right? But so mine crashes right away. But if you are close enough, it could orbit around the Earth 3 or 4 times, right? So that would be in the case where it's moving too slowly or it's too close to the Earth. Okay, so those are the kind of three situations of the orbital dynamics. Now, before we even get started, I just want to say that these pieces of information are in your data sheet in Physics 20 in Alberta. So you will keep those in mind as you do the questions. Okay, so you won't necessarily be given these values when you're doing the questions. Like, it won't be said in the question itself. You are expected to look it up because it's a known value. Just like 9.81 meters per second square is a known value, same with these ones. So keep that in mind as you do these next couple questions. So I highly recommend that you pause the video right now and see if you can solve these two questions. And yeah, press play when you're ready. Okay, hopefully you were able to solve these questions here. Let's take a look together. For the ISS to have a stable orbit, how fast does it have to be moving given that it is orbiting this high above the Earth's surface? So it's a stable orbit and it's orbiting that high above the Earth's surface. Well, if it's a stable orbit, this is the piece of information that we're going to use. FC equals FG. Okay, that's helpful because FG is G M1 M2 over R squared, right? Now, M1 is going to be the mass of the Earth. M2 is going to be the mass of the satellite, or I'm going to even write ISS, okay? So those are our two masses. Now, if we look at FC, this is going to be given by one of the formulas up here. Now, since we're talking about how fast does it have to move, we're looking for the formula with velocity. So that's this one right here. So mv squared over r. Now keep in mind that this m is the m for the ISS. And this is helpful because that means we can actually cancel, basically by dividing by that on both sides, those two. We can also cancel this r with this one of the two r's that's there. Okay, so now we're left with this equation. V squared equals G ME over R squared. Now we can square root both sides, so we get V equals the square root of G ME over R, not R squared, sorry, R, over R. Okay, so we can plug in all of our different values for that. 6.674 times 10 to the negative 11. The mass of the Earth, which is 5.97 times 10 to the 24, over the radius of the Earth. Now this is key. So yes, it is the radius of the Earth, but it's not just the radius of the Earth, it's also the orbital distance, right? So plus 408 and then 123 because it's in meters. Okay, so that means the velocity must be, and now we're going to calculate this. So square root of 6.674 times 10 to the exponent negative 11, 5.97 times, times 10 to the 24, 6.37 times 10 to the 6. Oh, whoops. So plus 408,123 bracket. There you go. Okay, so that is our value. So 7,667. And this is meters per second. You can see that that's going pretty quickly, right? This is going pretty quickly around the Earth. Okay, so so that is question number 1. Hopefully you can see the process there. Maybe you didn't get that one. try the second question. See if you can get this one. Okay, so let's read this one. The moon has an orbital period of 27 days. Given this fact, how far is it from the surface of the Earth? Now, I'm going to tell you right now, the moon has a quote-unquote stable orbit. So it may not be perfectly stable, but it's stable enough over the course of millions of years. So we're going to call it a stable orbit. So FC equals FG, and it's really going to be the same process, except we're solving for the radius this time. So now we can talk about the mass of the moon. And so if we have the mass of the moon, V squared over R equals G. Oh, let's not use V squared over R because we know the orbital period. We're going to use the other equation. 4 pi squared, hold on, 4 pi squared R M over T squared. Okay, and that equals FG, which is capital G M Earth M Moon over R squared. Now, the wonderful thing about this is that the masses of the moon will cancel on both sides. Okay, but not much else does. And so we're looking for the radius. So we're going to move everything else over. So we're going to divide by 4 pi squared over t, and we're going to multiply by r squared on both sides. So GME over, and t squared, over 4 pi squared, just like that. So this is going to be pi cubed equals GME t squared over 4 pi squared. So now we can square root, or cube root both sides, cube root both sides. So it's going to be GME t squared 4 pi squared. So this is going to be a little bit of a process here in the calculator, but follow along and you will hopefully understand. So we've got the cube root. We've got the fraction, 6.67 times 10 to the negative 11. Times the mass of Earth, which is 5.97 times 10 to the 24, times the time, which is 27 days, but there are 24 hours per day, and there are 60 minutes per hour and 60 seconds per minute. So we need seconds, right? So that would be roughly correct. And then 4 times pi squared on the bottom. Yeah, I didn't square the time. So we need to go back to this equation and make some adjustments. So we're going to go back all the way to here and insert bracket, and square that. I forgot to square my time. So now we're talking. So this is 1, 2, 3, 4, 5, 6, 7, 8. So times 10 to the 8. This is 3.80. Okay, yeah, so we're going to call it there. Now, this is in meters. Now, we were asking about the surface of the Earth. So, if we're talking about the surface of the Earth, we do have to subtract by the actual Earth's radius. So we're going to subtract by 6.37 times 10 to the 6. Now, it's not going to make a significant difference because we're at times 10 to the 8, right? But we'll do it anyway just to show how little of a difference that makes. So we're actually at, it does make a difference, just not a significant one, times 10 to the 8 meters. And actually with sig digs, we're talking 3.7 times 10 to the 8 meters as the correct answer. So let's just verify that. Distance to the moon, 3.84. Okay, yeah, pretty close. Close enough that, 27 days is probably not very accurate, so close enough. All right, 2 more questions for you to try. Pause the video and see if you can get them. Okay, looking at the next one, satellites need to have decaying orbits for them to be allowed in space. The reason why we don't want to have more space junk than we already do, because it is becoming more and more dangerous for astronauts in the ISS, not only ISS, but also the ISS, or spacewalks or whatever, getting hit with space debris. Given a geosynchronous orbit, meaning it orbits once per revolution, per revolution of the Earth, I should say. Okay. How far away from the planet would it have to be to ensure that it decays? So this is actually very similar to the last question here. We're wanting it to decay though, so we're saying that force of gravity is greater than the centripetal force. So, I mean, we're basically doing the exact same process, except that we're solving and having it saying at the very end saying anything less than the radius of blank will work. Now, usually it's a decaying orbit that will take like a couple years, like 10, 20 years to decay, but it is still a decaying orbit. I'm just trying to finish up here, so we're getting this value, and then it'd be R is less than the cube root of G M E T squared over 4 pi squared. Okay, so then we're going to say R has to be less than, and we're going to do kind of the same sort of calculation as before, except that instead of 27 days, we're talking 1 day. So just 24 hours. Other than that, everything else is actually the same. So we get a result of 4.22. 1, 2, 3, 4, 5, 6, 7. So 4.22 times 10 to the 7 meters. So it's actually pretty far away from the Earth for a geosynchronous orbit. So that's actually towards the center of the Earth, right? But actually, same idea as before, we should subtract by 6.37 times 10 to the 6. Now, because they're a little bit closer, it will be more important that we subtract, because they're like times 10 to the 7 times 10 to the 6. They're a little bit closer together. So it'll be 3.59 times 10 to the 7 meters. All right, now this is actually not equals, this is less than. So radius has to be less than that. Okay, last question. Starlink satellites from Elon Musk are placed in low Earth orbit at a height of roughly 550 kilometers above the Earth's surface. Given this fact, what is their orbital period? Okay, so we'll say that they're stable orbits. We don't know that for sure, but let's pretend. Okay, so this is going to be the same sort of equation as before, but this time we're looking for the orbital period. So this is actually going to be like yeah, I guess we could take a step from here and just go MAC equals MG, and then cancel out those, and then go further. So this is AC, and this is G. So I guess that probably is better to do than what I've been doing. Just a little bit less work. Anyway, so we're at this point. Now we're going to solve for t squared, and this should be equals. So we're going to solve for t squared, so we're going to move that over, we're going to move this over, we're going to move this down. So we're going to have 4 pi squared r cubed over g me equals t squared. So we're going to have t equals the square root of 4 pi squared r cubed over g me. So t equals, and so this is the orbital period. So second function, square root, 4 times pi squared times the radius, which is, keep in mind, the radius of the Earth's surface, like just like the radius of the Earth, so 6.37 times 10 to the 6. Okay, plus the orbital height, which is 550 times 10 to the 3, because it's in kilometers, you want to change it to meters. And then this is cubed. Okay, now we can go down to the bottom. We're going to go 6.674 times 10 to the exponent negative 11. And then the mass of the Earth, which is 5.9 something. 5.97 times 10 to the 24. And I believe that's our final answer. So the orbital period is 5,730. And this is seconds. Now, this is nice. You can probably leave it there, but to make it a more useful number, let's take that number and divide it by 60. Okay, so that would tell you how many minutes it is. So this is 90, what did we say, 95.5 minutes. Or, 1 hour, well, we could just divide by 6. 1.59 hours. Which equates to just, 1 hour and 35.5 minutes. Okay, so any one of those results are perfectly fine. This is probably the most usable number, just in terms of like prettiest to answer with. But all right, so I hope this video helped you better understand orbital dynamics, especially this concept of decaying versus satellites leaving the orbit versus a stable orbit. I hope this video helped, and good luck.